Just want to finish off looking at this motion stuff by looking at a handful of questions that have appeared over the years, going right back. I mean, this one was 1992, but different sort of looking problems. This one in 92 caused a bit of a fuss at the time because the syllabus says we only deal with constant angular velocity. But this question actually had variable angular velocity in it. And they got away with it because if we have a look at what the problem is, we've got a lovely circular railway track here and the train is going around it with constant angular velocity. So it is constant angular velocity. Problem is when you take a different reference point, so the point here, n, that also sweeps out an angle, but that angle wouldn't be changing in a constant amount. It would be variable. So it works through this problem. So our train going around the track's got radius A, constant speed, u meters per second, n is on the same plane, fancy way of saying I guess they're sitting on a table or something like that, and is x meters from the nearest point on the track. NO produced meets the track, so the other side of the diameter, if you like, is S. So they've defined TNS to be phi, TOS to be theta. Okay. So the first thing is they want us to work out the theta to t in terms of A and U. Well, we know length is equal to, the length of the arc is equal to the radius times theta. In this case, the radius of our circle was A. So length is equal to A theta. So dl dt would be A times d theta dt. But dl dt, that would be our linear velocity, and we define that to be u. Rearranging to make d theta dt the subject, and we simply get u over A. Okay. Now for the easy bit. We're going to show this lovely expression here. A sine theta minus phi minus x plus a times sine phi is equal to 0. And then from that deduce that the rate of change of phi with respect to time is this beautiful expression, which, as I say, it's not a constant. It turns out to be something quite different. If you have a look at the original diagram, I'm going to have to define a few things in order to show this. So angle NTO and TNO would equal TOS, exterior angle of the triangle. And so substituting in the phi and the theta, I can say, well, okay, angle NTO is the theta minus phi. Looking at what I'm trying to prove, I had to identify an angle that was theta minus phi. And so there it is. NTO would be theta minus phi. Now have a look at triangle NTO. What we're basically now doing is simply the sine rule. It just looks a bit different. So if you look at NTO, A over sine phi is A plus X over sine theta minus phi. Well, all we now got to do is cross multiply, move everything to one side, and we've got the expression that they want. So it looked quite terrible, but really it was just the sine rule, applying the sine rule to the triangle. It's the next bit that becomes interesting, finding phi to t. So I'm now going to differentiate that with respect to t. A, of course, is a constant. Now that cosine function, I can't differentiate it with respect to t, but I can differentiate it with respect to theta minus phi, whatever that function is. But then I'd have to multiply it by the theta minus phi to t. But I've actually split that up to be the theta to t minus the phi to t. Because remember our rules of differentiation, if we've got several things added together, we can differentiate each bit individually. So the theta minus phi to t, I can split up and do each bit individually and go, oh, well, that's the theta to t minus the phi to t. Minus, so then we get to the other bit, a plus x, and again, that's just a constant. Cos of phi, can't differentiate it with respect to t, but I can, oh sorry, it was sine of phi in the original one. Can't differentiate it with respect to t, can do it with respect to phi, so I have to then multiply by the phi to t. We're trying to make the phi to t the subject of all this. So let's group the phi to t's together and the theta to t's together. Well, there's only one term in there that's times the theta to t, that's the a cos theta minus phi. Then everything else is actually times the phi to t. And so I've grouped it and gone, well, that's minus a cos theta minus phi plus a plus x cos phi. Okay, remember we're trying to make the phi to t the subject, so I'll move that to the other side. Now, the other thing I've done, the theta to t, well, we've already proved that earlier to be u over a. So I've substituted that in. Dividing by the a cos theta minus phi and plus a plus cos phi, and we actually do get the result. Quite a tricky little derivative to handle there. Okay. Show that when divided t is equal to 0, then nt is actually at a tangent to the circle. So when that rate of change of phi is 0 or stationary, then nt is a tangent. Let's draw the actual picture up. So they're saying nt is a tangent there. So when nt is a tangent, we know things like the radius will be perpendicular to the tangent. That becomes a right angle triangle. So NTO is a right angle. So theta minus phi, because remember that was the angle we called theta minus phi, is 90 degrees. So if I sub that into what we just found for theta t, on the top of the fraction, I get cos of 90. I suppose it doesn't really matter what's on the bottom of the fraction, because as soon as the top of the fraction is multiplied by cos 90, and cos 90 is, of course, 0, then theta t is 0, and that's what we're trying to prove. So there it is. Now, suppose that x is equal to a. We're now going to show the train's angular velocity about n, so that's the phi to theta t, when theta's pi on 2 is 3/5 when theta is equal to 0. So let's investigate when theta is pi on 2. So again, we'll draw up that triangle, but now theta is pi on 2, so angle NOT is the 90 degrees now. OT is the radius, which we've defined to be a. ON will now be 2a, because we've said x is equal to a. So from there, we can get a value for tan phi, cos phi, sin phi, whatever we need. So the hypotenuse will be root 5a. So cos phi will be 2 on root 5. Cos of 90 minus phi, because NTO would be our 90 minus phi, is 1 on root 5. Substitute that into the expression that we found, and we end up with, and changing over here, it was a plus x before, but now that's 2a. So I get u times 1 on root 5 over a times 1 on root 5 plus 2a times 2 on root 5. I can multiply everything by root 5, do some tidying up, and I get u on 5a. So there's the value when theta is pi on 2. Now we're going to see what it is when theta is equal to 0, and hopefully one will be 3/5 times the other. So when theta is equal to 0, well, when theta is equal to 0, let's sub it in. What's it going to be? If it's 0, we're now talking about a straight line, aren't we? Because remember, theta is this angle NOT. So if it's 0, OT and NO are on top of each other. And so the 90 minus phi will be 0 as well, because it's lying on the line. And so all those angles basically are 0. So subbing in, cos of 0, of course, is 1. And I get u on 3a. Remember, we're trying to show one of those is 3/5 times the other. So now it's just a little bit of algebra there. Well, u on 3a is the same as saying 5/3 u on 5a. So yes, that one is 3/5 times the other. Let's have a look at this problem. This was a vertical circle. So strength of length L is initially vertical, so it's just hanging straight down there along OA. Mass P is given a horizontal velocity of v, and so it ends moving in a circle, and we're saying we're going to go in a counterclockwise direction. O is the centre of that circle. As I say, A is the initial starting point down here. For some reason, they want to use S for the length of the arc instead of L, but that's fine. Whatever you want to use, they want to use. Velocity then becomes ds to t instead of dl to t. The angle at the centre is theta, so angle AOP. Tension, because it's attached to a string, so there'll be tension going up the string, so that's T. Acceleration due to gravity is G. We will assume no frictional forces to make the problem a little bit easier. For parts A to D, we are going to assume the mass continues to move in that nice circle. So in part A, they want us to show the tangential acceleration of P is given by this wonderful expression. D2s to T2, so that's the linear acceleration basically, or tangential acceleration. 1 on L, d to theta of a half v squared. What we're basically proving is the acceleration is d dx of a half v squared, but we're proving it in this circular motion. So I'm going to do it a similar way. Okay, S is equal to L times theta. I guess that explains why they couldn't call the length of the arc L, because they'd already called the string L. That would confuse things, obviously, if they were both L. So S is equal to L theta instead of L equaling R theta. Velocity is ds to t. So in ours, it'll be L d theta to t. That's going to be our linear velocity. So acceleration we know is dv to t. So I'm going to rewrite that as dv d theta times d theta to t. You may recall this is the sort of thing I ended up doing, proving the d dx of a half v squared. Same steps. And then I'm saying, oh, well, hang on, but d theta to t in this case, I can write as v on L. Because over here, rewriting that one. So I now have it is v on L times dv d theta. That's how we get the L into our answer. I can factorise that out. All I now need is the d d theta of a half v squared. But v, of course, I can rewrite as d to v of a half v squared. The dv's cancel, and so there it is, 1 on L d to theta of a half v squared. So the equation of motion of P is given by that. Lovely expression. So what we've just proved is going to equal minus g sine theta. Well, let's draw up our problem. There's good old Bob. Okay. The tension is going towards the centre of the circle, up the string. I've made it a horizontal force, so I can look at things and think of horizontal and vertical. Of course, I've rotated the problem, so gravity is no longer going straight down. It's going off at an angle, which means I have a component of gravity. Now that's assuming the bob is in the picture, the position as described in the picture. I mean, at some point, it will be horizontal, but I'm just going off the diagram they've given us. Okay, so looking at what looks like vertical forces, I'm going to have an mg sine theta going down and nothing going up. So it'll be my resultant force going up, which is the linear one, because it'll be at right angles to the tension. So right angles to the tension would be the linear acceleration, that ms double dot. So ms double dot is going to equal minus mg sine theta, but if I cancel the m's, I now get the linear acceleration, which is what we just proved before, is 1 on L d to theta of a half v squared. So all I now do is substitute in, and I've got our results. So we're going to deduce from that from capital V squared is equal to little v squared plus 2gl 1 minus cos theta. Okay, let's start with what we just proved. We're trying to get an expression. So let's get rid of the L, multiply it by the other side. I've now got d to theta of a half v squared is minus gl sine theta. So I've got it in terms of theta. So a half v squared will be gl cos theta plus c multiplied by 2. Let's find that constant. What do we know? When theta was equal to 0, they told us the initial velocity, you may remember it was going off with capital V, the velocity. So subbing that in, my constant becomes v squared minus 2gl. Subbing that in, a little bit of factorisation, and we get the lovely expression that they want us to look at. Okay, but there's more. Explain why T minus mg cos theta will equal 1 on L mv squared. Okay, back to Bob. Remember, there's the tension. Mg cos theta, we now know, is going the other way. Okay, and there's the resultant force. The resultant force in circular motion is, of course, mx double dot, the resultant force, which, oh, what's that? Resultant force. It's going to be tension minus mg cos theta. The question might give you a hint. Half m. The resultant force is centripetal force. Remember, circular motion, the resultant force towards the centre is always centripetal force. So if I sub that in, mv squared on r, but in this case r was L, and we can rearrange it, and there it is, our expression that we wanted. Now, suppose that v squared is equal to 3gl. Find the value of theta at which the tension is equal to 0. Okay, let's sub in v squared is 3gl. So T minus mg is a half m little v squared, but back in part C, we said little v squared was capital V squared minus the 2gl, 1 minus cos theta, but v squared is 3gl, so sub that in. Tension, we're saying, is 0, so I now have minus mg cos theta, 1 on L m, 3gl minus 2gl minus 2gl cos theta. That tidies up. So I've now got 3 mg cos theta is equal to minus mg. Cos theta is minus a third. So I can now go and find the value of theta. Cos theta minus a third. So in radians, 1.91 radians. How far around the circle have we gone? We've gone less than halfway. Because, of course, in a complete circle, there are 2 pi radians. Therefore, in half, there would be pi radians. Pi is approximately 3.141592653 any opportunity. 897932, and so that would be less than. Right. Back to part F. These are the questions I know you love, where you have to describe what's happening, because I know how you enjoy these sort of things. Consider the situation in part E. Briefly describe in words the path of our particle after the tension becomes 0. So you're spinning an object in a circle, but it's tension that's making it go in the circle. But all of a sudden, at some point, there's no tension. What's going to happen? So, when tension is equal to 0, the only force acting on the particle is now gravity. So we have our classic projectile motion situation. It's going to go off in a parabolic arc. Okay? But it won't finish projectile motion. Because when it's in its parabolic arc, at some point, it's still attached to that string. And so at some point, the string will go tight again, and tension will come back into play, and it'll go back into circular motion again. Okay? So, let's have a look. Tension is now going to be 0, so let's sub it in. Cos theta we know is minus 1/3. Anyway, the velocity, again, I might have gone overboard with describing this one, but I've gone and found the velocity that it goes off at. It goes off with the velocity of the square root of GL on 3. And here's a picture of it. There's the circle. Right, watch this, you're going to love this. Starts at the bottom, goes whee, in circular motion for about 1 point something radians, which we know is less than half. We're getting to the point now where tension becomes 0. So it's going to shoot off with a velocity at an angle, but it'll go off like a parabola. But then at some point, tension will kick in and it'll go back into the circle again. Ta-da! Oh, hang on. Let's go back to there. I thought I wrote something. So there's my description. Let's have a look at this 2003 problem. 2003 problem was really cool because it's projectile motion, but taking resistance into account. which of course we don't do in the 3-unit model. So that's why our projectile no longer looks like a parabola, because of the resistance coming into play. But they help us out a bit by giving us the different equations. So acceleration in the horizontal direction will be minus some constant times velocity, because that's basically the resistance in the opposite direction. Gravity is still there, minus g, but it also has resistance in the opposite direction, so minus k times the velocity. These sort of notes are very important. You are not required to show these, right? They're giving you that information. Be amazed how many people try and prove it. Okay. Derive the result then. So our horizontal velocity will no longer be constant. It'll now be u e to the minus kt cos alpha. So let's start with our acceleration, which we said was minus k x dot. So therefore t, I've done a definite integral, and it's going from an initial velocity. The initial velocity is still the same. That's still u cos alpha, up to some random velocity that we're trying to find. I took minus 1 and k out as a constant, and we just got our log function there. So dx dot on x dot. Integrate that, we get the log of x dot. And so I've got the log of x dot minus the log of u cos alpha. Minus kt becomes the log of x dot. Undoing the log, we exponentialise. Now we can get rid of the u cos alpha, and we've got our expression for the velocity. They haven't asked us, no, it gets funnier. They haven't asked us to actually prove this. Guess how I did it? I actually went and proved it. But it just says verify that it satisfies the equation of the motion. So it would have been a heck of a lot quicker just to differentiate that and show it satisfies, but I didn't do that. I went and derived it. Y dot to t. So definite integral, same sort of idea. Another log function, but this time it's ky dot plus g log. Because, yeah, you don't need to do all this because it's just saying verify. It's not saying prove. So you can just differentiate it and go, oh, look, it does satisfy the equation of motion. But I just thought this was impressive. And then we play around with it. Ta-da! It works. That's the long way of doing it. Right? The quick way would have just been to differentiate that expression there and show, oh, look, it does equal to, what was the expression we had? Minus k y dot plus, whatever. Silly boy. Find the value of t when the particle reaches the maximum height. Well, these sort of things don't change. Maximum height is still going to be when the vertical velocity is equal to 0. So we just need to solve that. I've done it in, so remember we had, I'll go back a slide, rather than going straight from the y dot formula, at some point, there it is, we have an expression that allows us to find time. So I've gone back to that point and just changed y dot to be 0, because we're saying I'm going up to a velocity of 0. So that's why, rather than making I did make y dot equal to 0, but I made it equal to 0 in that expression there because it's time that I'm trying to find. Subbing in, and there we go. 1 on k log ku sine alpha plus g all over g. But you probably would have guessed that. What is the limiting value of the horizontal displacement of the particle? Okay. There's an expression we've got so far for horizontal velocity. Let's go find an expression for horizontal displacement. But we want the limiting. So t will approach infinity. Now, u cos alpha, that's all constant. So I've taken that out the front of the integral. That's actually a really bad way of writing the integral. I shouldn't write 0 to infinity there. I should have put a t at the top there. Because we're saying as t approaches infinity, the integral 0 to t I should have put. Or possibly even use another letter. But let's go and find that limit. And we end up with an exponential, which of course approaches 0. And so I just end up with the u cos alpha over k. All right. Cambridge. The Cambridge questions you will notice for this last bit are just a rehash of HSC questions, pretty much the same ones. In some cases, the same ones we just did anyway. Patel's got a handful, and 9F's grab a few out of there as well.